Okay guys, this is section 5.4. In this section our goal here is to be able to factor and solve other polynomial equations. So thus far in earlier chapters we talked about degrees of 1 or degrees of 2 being the highest exponents. So now we're going to look at degrees or highest exponents of 3, 4, and on and on. So we had some general kind of expressions that we talked about in earlier chapters, like the general trinomial and how we would factor that. Okay, we used the x method and got two factors out of it. We also factored perfect square trinomials, and we got to where it looked like a factor squared. And again, all that means is there's really two factors hiding in there. But since they were the same thing multiplied together, we could just rewrite it as this factor squared. Okay. The difference of two squares we actually talked about as well. Okay, remember that the difference of two squares always has a factor that was a plus and a factor that was a minus. And lastly here we have a common factor, monomial factor. Okay, all this does is we're looking at both of our terms and seeing, what's common or what could we pull out of both of those terms? Well, 8 and 20 both share a factor of 4. So we could pull that out of there, and they both have at least one x, so we could pull that out of there as well. Okay, and in order to fill out what was left of those factors, well, 8 divided by 4 was 2, and we took away one of the x's, because there was only two of them. And 20 divided by 4 is 5, and we only took one x out of it, so we don't have any more left. So that's where they're getting this 4x times the quantity 2x plus 5. And again, if you were to FOIL it, or not FOIL, but distribute it back, you would get 8x squared plus 20x. So we were just factoring out a common factor out of both of those terms. But if we want to factor completely, a polynomial with integer coefficients is factored completely if it is written as a product of unfactorable polynomials with integer coefficients. So we're going to look at how we can factor completely some polynomials. So for example, the first thing I want to do is look across my terms in my polynomial and see, can I factor out a common factor? Okay, well, my coefficients here are 1, 2, and negative 15, and they don't share any common factors across all three of those, so I'm not going to pull out any numbers, but they do share at least one x, so I can pull an x out of all three of those. Okay, if I pull an x out of the first term, I'm left with x squared. In the second term, I'm going to be left with 2x, I just got rid of 1x, and then I'll be left with negative 15. Since I pulled that x out of the negative 15x term. Okay, now I need to look, well, stuff inside my parentheses, can that be factored down? Well, yeah, it can. And we could test that with the x method that we talked about in chapter 4. Okay, remember, I take my a times my c, 1 times negative 15 is negative 15, and in the bottom I'm putting my b, which is 2, and my factors that help me add the 2 but multiply to negative 15 are 5 and negative 3, and I'm putting x on top. So this tells me my factors can be x plus 5 and x minus 3. And now we say that's factored down completely for that expression there. Same thing with this one. We're going to see, can we pull out any common factors? Okay, so looking across here, my coefficients first. Well, 2 and negative 18, they're both even, so I can pull at least the 2 out. And looking at the variables, okay, I have at least 3 y's in both of them, so I'm going to pull out 3. And if I pull that out, well, I'm left with 2 y's from my 2y to the 5th term, and my negative 18y to the 3rd power, I'm just left with negative 9, because I pulled out all 3 of the y's. Okay, but checking to see, can that stuff inside the parentheses factor all the way down? Yeah, it can. If I do the x method again, I got negative 9 up top and 0 in the bottom because my b was 0. So, negative 3 and positive 3 help add to 0 but multiply to negative 9. And if I put y on top of those, here are my factors. I'm going to drop down that 2y to the 3rd power, but y squared minus 9 factors all the way down to y minus 3 and y plus 3. Okay, and again, that was a factor of two perfect squares, okay, or a difference of two squares, because y squared minus 3 squared, okay, I'm going to have one that is a y minus 3, and the other factor needs to be a plus 3. So there's that y it should be factored all the way down completely there. And this last example here, again, I'm going to pull out any number that's common across all my coefficients, so 4, 16, and 16. Well, 4 can go in all of those. And looking across my variables, I could pull out 2 z's at the most out of all three of my terms. And if I go back in there, well, with the first term, I'm only left with 2 more z's. The 4 went away. Negative 16 divided by 4 is negative 4. And I'm only left with 1 z. Okay, you could choose whether or not to write that exponent of 1. And then 16 divided by 4 is 4, but you already pulled out both of those z's. So you don't have any more with that term. Okay, and the last step there, can I see if that stuff inside the parentheses can be factored? Well, yeah, it can. We're going to test that out. So 1 times 4 is 4 up top, and negative 4 goes in the bottom. My factors that help add the negative 4 and multiply to 4 are 2 and negative 2. And we're putting the z's on top. So if I drop down the 4z squared, I have z plus 2 and z minus 2. Okay. Alright. So that is our expression factored all the way down completely there. So we also have some other special factoring patterns for cubes or exponents of 3. So if I take the sum of 2 cubes, okay, my pattern's always going to look like this one here. So it's always going to be handy to keep these around when you're doing problems that have a sum of 2 cubes and also a difference of 2 cubes or subtracting 2 cubes. Okay, so there's 2 patterns that go along here. For example, if the sum of 2 cubes, I have 8x to the cube power plus 27. Well, that's really the same as 2x cubed that we're getting right here. And 27 is a perfect cube. 3 to the third power is 27, so that's where they're getting 3 here. So their first term of a, which is 2x, goes first, and then their term of b, which is 3, goes next. So that's their first factor there, 2x plus 3. Then they're getting this whole part in the parentheses from the second set of parentheses here. So we're taking the first term squared, okay, so that is 2x squared minus 2x times 3, which is the same as 6x, and then lastly the second term, or 3 squared, which was 9. Okay, so it's always good to kind of write it out and then kind of simplify that. Same thing with difference of 2 cubes. Okay, in this first part I have 64x to the third power. Well, that's the same thing as 4x cubed. And 1 is a perfect cube because 1 cubed is still 1. Okay, so again, my a, or my first term, was at 4x, so that's going there. And then b was 1, so that was going next. And it was going to be a subtraction in there, so that's my first factor. And then it goes my first term squared, or a squared, which was 4x squared, which is simplified down to 16x squared. Then we're adding the first term times the second term b, which is still 4x. Then lastly, the second term squared, or b squared, was 1. So that's how they're getting that factor that's inside the parentheses there. And then it's considered factored all the way down completely. So, in this first one, we have a sum of 2 cubes, and I already wrote down the pattern there that we just talked about. We have a factor of a plus b, or the first and the second term added together, times that other factor there. Okay, so if we follow along with that, our expression x cubed plus 64, well, that's already a cube of x, and 64 is a perfect cube too, okay? 4 cubed is 64, okay? So if I follow along with my pattern, my first term a in this case is x, okay? And then my second term b is 4. And if I try to follow along here with my second part of the factor here, okay, my first term squared, or my first term was x, and I'm squaring it, okay? Then I'm subtracting out my first term times my second term, which was 4, so x times 4. And then lastly, my second term squared, which is 4 squared. And if I simplify that, that becomes x squared minus 4x plus 16, because 4 squared is 16. So here we have our expression factored down all the way completely. Same thing with this next one. Okay, I have a difference here, but first, like we did in the first 3 examples, we're going to see, can we factor out anything first? Okay, so if I look across here, my coefficients are 16 and negative 250. Well, they're both even, so I can at least pull out a 2. Okay, and if I look at the variables, there's at least 2 z's in both of them, so I'm going to pull out 2 z's as well. Okay, so 16 divided by 2 is 8, and we're going to be left with 3 z's. Okay, because 5 minus 2 is 3. And then negative 250 divided by 2 is negative 125. And we already factored out both of those z's, so we don't have any more there. Okay, but now looking at this one, I now have a difference of 2 cubes. Okay, because 8z cubed is the same thing as 2z cubed. So my first factor term here is a, and then negative 125 is actually a perfect cube as well. 125 is the same thing as 5 cubed. So 5 is my term b. Okay, so if we kind of rewrite this up here using that info, my first term was 2z, and my term b was 5. So there's my first factor. And then my first term and my second factor here, a squared, that is 2z squared, plus my first term times my second term, 2z times my second term, 5, plus my second term squared, or 5 squared. And if we simplify that, well, that's 2z minus 5. That's not going anywhere as a factor. But 4z squared is coming out of that simplified 2z squared. And then 2z times 5 is just regular old 10z. And 5 squared is 25. Okay, but that's not my answer, because remember, I had this 2z squared that I factored out in the beginning. I got to put it over here with it. So my final factored out completely expression of my original expression is everything put together here. And again, these can kind of get confusing, but if you write them out, your patterns, okay, if you have them handy right there, and you figure out your term A and B and just follow the pattern and put them together in the end, it won't be so bad. Okay, so here's my final expression factored out all the way completely. The next thing we're going to talk about is how we can factor by grouping. To factor a polynomial with 4 terms by grouping, factor common monomials from pairs of terms, and then look for a common binomial factor. So for example, here we have some letters that are representing some integers here, okay, and along with some variables. The factor by grouping, we always try to group out, okay, and I always like to put parentheses around the first 2 and then the second 2. And if I notice here, in my first factor here, I have a common letter of R, so we factored out the R here, and we're left with a plus b. Same thing in the second factor here, okay? I have a common factor of s, so I'm going to pull that s out, and I'm going to be left with a plus b again. But if I notice here, I have two common factors here, a plus b and another a plus b. So I'm only going to write one of them. Okay, so that's coming from here. And if I notice my r and s, I can just combine those two. Okay, coming from right here. So my factored out form completely of 4 terms, okay, by grouping, we'll have just 2 factors in the end. So let's practice a couple of these. So with example 3, okay, we're going to factor this polynomial completely, and since I have 4 terms, I'm going to do it by grouping, okay? So first, I'm going to group them off by this right here, okay? And I'm going to see, can I factor out any of those in each set of parentheses here? So in my first pair, or my first parentheses set, I have x cubed minus 3x squared. Well, my coefficients are 1 and negative 3, so I can't pull any number out, but I can pull out 2 x's, okay, because that's the most they both have in common. So if I factor that out, I'm left with 1x minus 3, if I pull 2 x's out of there. Then, in my next set of parentheses, I'm looking at 16 and 48. Okay, I can't pull out any variables because they don't even have, both of them don't have variables, so I can't pull out any variables, but a common number that goes into both 16 and 48 that is the highest is actually 16. And if I pull 16 out of 16, I'm left with x, and 48 divided by 16 is 3. And in order to make it a positive 48, remember, negative 16 times a negative 3 gives me positive 48. That's why it's a minus sign right there. Alright, so now what I can do, is since these are both x minus 3's, I'm going to have one factor that has an x minus 3. Then, if I put together my x squared minus 16, that's going to be my other factor there. So I'm left with this right now. But my x squared minus 16, that's a difference of 2 squares. Okay, so I have x squared minus 4 squared gives me 16. So my first factor is going to be an x minus 4, but remember the other one has to be a plus 4. So over in here, that becomes x minus 4 and x plus 4. Then my other factor I just dropped down, that is x minus 3. And you could have even went and did the x method with x squared minus 16, because we got to make 0, and 4 minus 4 made 0. And you could have got your factors that way, but that was a perfect square for both those, x and 16, and it was a difference of 2 squares, or subtracting 2 squares. So we did the method that way, and finally got it to be factored completely in the end with those 4 terms. Alright, quadratic form is the form au squared plus bu plus c, where u is an expression of x. So we're trying to get these in quadratic form here. So this first example here, well, I'm going to factor this completely. The first thing I notice right off the bat, I have some perfect squares going on, 16 and 81. Okay, so 16x to the 4th, 4x squared to the 2nd power gets me back to 16x to the 4th. Okay, so 4x squared was that term. Then if I drop down 81, I know 9 squared is 81, and I'm bringing down that subtraction sign. And remember, for a difference of 2 squares, it's coming from inside those parentheses, those terms, so 4x squared minus 9, and remember my other one has to be a plus 9. Okay, and now, if I look here and see if I can simplify any of these down, well, 4x squared plus 9 can't, but 4x squared minus 9 can. So let's do the x method with that one. 4 times negative 9, remember a times c, negative 36 up top, and my b is 0, since I don't have any b term. So my factors there are 6 and minus 6. That help make 0, but multiply to be negative 36. And up top, remember, I'm not just putting x, because my a in this case is 4, so I'm putting 4x on top of those. And since 4 and 6's are both even, I'm going to divide each side by 2. So 4 divided by 2 is 2x, and negative 6 divided by 2 is negative 3. So here's one factor. And then 4 divided by 2 is 2x here, and 6 divided by 2 is 3 for this factor. So on this side, I have a factor of 2x minus 3 and 2x plus 3. Then I'm going to drop down my other factor I couldn't factor down anymore. So 4x squared plus 9. And here is that factor down all the way completely for that expression. Another one here. Well, I want to think about, can I pull out anything out of all three of my terms? Can I factor out anything yet? Well, yeah, I can, because my coefficients are all even, so I could at least pull out a 2. And I could at least pull out 2 p's, because that's the most that they have in all three of those. So if I factor out those, I'm left with 6 p's in my first term, and 5p to the third power, my second term, and just regular old 6 in my last term, because I already pulled out 2 of the p's already. Okay. Now I'm left with this factor here, p to the 6th plus 5p to the third plus 6. I could actually take that to the x method and see what I get out of that. Okay, so 1 times 6, or a times c, is 6, and my b is 5. Okay, so trying to make 6 when multiplied and trying to make 5 when added, my factors could be 3 and 2. Okay, but here is the tricky part. Since I have 2 factors, I want to put a 3 with these. Basically going to split it in half. So p to the third power. So that 6 is coming from right here. So I'm going to make it split in half, because I'm going to have 2 factors. Okay, outline that a little bit better. So I'm going to drop down this 2p squared. And then my first factor is going to be p to the third power plus 3. And then my second factor is p to the third power plus 2. And that's actually factored all the way down completely here. Okay? Alright. In example 5, we have, what are the real number solutions of this equation here? So first I want to make sure it's set equal to 0 first. So I'm going to move that the 18x to the third power to the other side, and put it in between those two first terms so that we have it in standard form. So 3x to the fifth power minus 18x to the third power plus 15x equals 0. Okay, and I'm going to first see, can I factor out any monomial out of all three of those terms? Is there something in common in all three of those terms? Well, if I look across my coefficients, I got 3, 18, and 15. I can factor out a 3. And then looking at my variables, I can at least pull out 1x, because that's the most they have in common variable-wise out of all three of those terms. So I'm going to pull out a 3x, so I'm going to be left with x to the fourth. Negative 18 divided by 3 is negative 6, and I'm left with 2 x's. And then 15 divided by 3 is 5, and I already pulled out its x. Okay, so now I'm going to take that new polynomial inside the parentheses, and I'm going to use the x method on that. Okay, so again, 1 times 5, my a times c is 5, and my b in this case is negative 6. And in order to make those factors there, I need negative 5 and negative 1. But now I'm going to put x squared up top, because I'm going to again split that x to the fourth in half. So I'll kind of highlight there again. I'm making these split in half to be 2 because I need a 4 there. Okay, and I don't need to simplify anything down, because my coefficient was just 1 there. There we go. So I'm left with 3x and then x squared minus 5 and then x squared minus 1 equals 0. So now I got to see, can any of these factor down? Well, 3x can't, x squared minus 5 can't, but x squared minus 1, that is actually a difference of 2 squares. Okay, so I'm left with x squared, and 1 squared is actually, again, just 1. So again, I'm going to have one factor that's a negative, or a minus 1, and the other factor will be a plus 1. So I'm left with 3x, x squared minus 5, x minus 1, and x plus 1 equals 0. And again, you could have did the x method on that and got -1 and b 0. Okay, and we need 1 minus 1 to be 0, and the x is on top, so x plus 1 and x minus 1. But that was a difference of squares there that we pulled out of that. So now we got to find the real number solutions, or the zeros, or the roots out of this. Okay, so what I'm going to do is break each one apart and set it equal to 0. So 3x equals 0, x squared minus 5 equals 0, x minus 1 equals 0, and x plus 1 equals 0. So if I solve this first one and divide both sides by 3, x is still going to be 0. If I add 5 here to this one, and then take the square root, remember I need the positive or negative case of square root of 5. If I add 1 to the other side here, I just get x to be 1. And if I subtract 1 here, I get x to be -1. So there's really 1, 2, 3, 4, 5 solutions here. Not 4, because we have this case of plus or minus with that square root of 5. So these are the 5 solutions, or real number solutions, of this equation after we factored it all the way down completely.